Last time we studied, we start waveguides, and we derived it for the waves in the waveguides a group velocity and phase velocity. So group velocity has a value less than the value at the infinite space. If there is no walls, if we have a plane waves in the infinite space, the group velocity is 1 over square root of mu 0 epsilon 0, that is the speed of light, and that is equal to the phase velocity. And for the phase velocity in the waveguide, the phase velocity is greater than the phase velocity in the infinite medium. So today I want to finish this chapter quickly, and I want to start to the radiation. So we said that last time the information in the waveguide travels by the group velocity, and that is due to the reflection of the waves from the walls of the waveguide. And we estimate that the power transmitted in the waveguide, and the power transmitted in the waveguide is nothing but the Poynting vector dot product from with the z-axis integrated through the cross-sectional area. So here, this is the z-axis, and we have x, y, and z. So S is a Poynting vector, energy per second per area. If you look at the projection along the propagation and integrate from the cross-sectional area, you will get energy per second, and that is the transmitted power. And transmitted power travels at the group velocity. And practically, the walls of the waveguide are not ideal, so they are not perfect conductors. So therefore, there are some attenuation in those waves. So we can calculate the attenuation coefficient using the very simple argument. We know that the z component of the waves are traveling waves, e to the plus or minus k z. For positive z-axis is plus, and for negative is minus. K is the wave number. So if there is some attenuation of the waves during the travel in the guide, we can have what? We have some decay, and that decay could be expressed a new wave number, which has the real part and imaginary part. So if you have this kind of solution, if you insert there, you have oscillatory solutions for the traveling waves, and you have also exponentially decaying solution. So if you substitute here, I times I will be minus I, and that will bring us the decay of the waves during the travel through the waveguide. So basically, if you have such wave number, real plus imaginary part, your electric field or magnetic field in the guide has the z component e to the plus minus k plus I beta z. So the transmitted power then goes as what? The power here is proportional to what? Transmitted energy, and it is related with the energy density. Energy density is related with what? Energy density is related with, in terms of the fields, energy density is square of the amplitudes, E square or B square. So basically, your power should be proportional to the transmitted power as a function of Z, proportional to the some initial power and exponentially some term. So what should be that exponential? So this power should decay during the guide's travel in the waveguide. And that decay is related with the attenuation coefficient. And power is related E square or B square. Therefore, square of this term, what is, if you take the square of this, what you are going to obtain? So this is equivalent to what? Some E or B, e to the plus ikz, e to the minus beta z. So if you take the square of this field, one of the field, it doesn't matter, this will be unit because you will multiply with the complex conjugate, and this will be a factor of 2, e to the minus 2 beta z. So basically, we will put the form of the power transmission in the following form: 2 beta z. Beta is the attenuation coefficient. There's a factor of 2 here because our fields exponentially decay, and the energy density, transmitted energy, goes with square of the absolute square of the E square or B square. Therefore, if we say that our wave number is k plus I beta, and the square will be the what? E to the minus 2 beta z. So basically, the power transmission will decay as a function of z in the waveguide exponentially. And how we can find the beta? Beta is the attenuation coefficient. So the calculation is the beta is very easy. If you take the derivative of the transmitted power with respect to the z, what you are going to obtain? Minus 2 beta times exponential term. And if you divide this to the same quantity, 2 times p, and multiply with minus, you will get the beta. And beta is the attenuation coefficient. So you can see by hand. So if you take the derivative, you will have minus 2 beta times the same quantity. Divide to the same thing here. That will be, these up and down terms will be cancelled. 2 will be cancelled, and you will obtain the beta. So if we assume that the power transmission decays exponentially, and then you can find that the exponential coefficient very easily, and that is nothing but the attenuation coefficient. So I am not going to derive this. I will show you how you are going to calculate it, because I don't want to waste too much time in details. So what we have seen that in the first lecture of this chapter, we investigate the behavior of the electromagnetic waves near the conductor. And if you remember, we find some expression for the power loss per area at the surface of the conductor. That expression was equal to 1 over 2 conductivity times the skin depth n cross h square. So basically this term this is the conductivity, this is the skin depth, and if you look at the open form, the situation is the following: 1/2 magnetic permeability frequency over 2 sigma, and that was equal to 1/4 mu frequency times the skin depth. So you are just substituting the definition of the skin depth in terms of conductivity, and then conductivity enters the square root of 2, and you are obtaining the expression in terms of the skin depth. So basically, if you do carefully this, when the skin depth goes to 0, the power loss per area goes to 0. So look at your notes. We derive this. So basically, we can calculate the power loss per length using this. How we can calculate? The area is the area element on the guide, and that is nothing but dz times dl, and dz is the propagation element in the z direction, and dl is the arc element on the guide. So if you write the area element as dz times dl, then you can obtain that the power loss per length is a integral. So if you integrate this through the cross-sectional length at the surface of the guide, you will obtain an expression in the following form. So that will be 1/2 sigma times the skin depth and cross h square and integrated through the dl. So basically, we have to calculate the n cross h through the surface of the guide, and that will give us the power loss per length. And if we divide, we have the power loss per length, and we have the power, and if you take the ratio, we can estimate the attenuation constant easily. So let me show you quickly how you are going to estimate this. So last time we studied for TM waves. Transverse magnetic waves, and we estimate the power. So what was the power transmission? So that was the transmitted power. If you look at your notes for TM waves, that was equal to S dot Z through the cross-sectional area of the guide, waveguide. That was equal to omega k over 2 gamma square epsilon Ez square evaluated through the cross-section area. So this was for TM waves. So the property of the TM waves, what was the property of the TM waves? The BZ component is 0, but EZ is not equal to 0. And what was our aim? We find that the EZ component by solving the wave equation, and then we estimate that the pointing vector, and we look at the projection along the propagation direction, and we integrate it through the cross-sectional area, and we find that the power transmission is related with the square of the z component, and the power is transmitted, as I said earlier, with the group velocity. Now what I am trying to do, I am trying to calculate, to show you how you are going to calculate the power loss per length. And in order to calculate the power loss per length, we use that the behavior of the electromagnetic waves near the conductor, and we have shown that the power per area, loss per area at the surface of the conductor is related with the skin depth. So if the skin depth goes to 0, there is no power loss on the conductor, but if there is a skin depth, that is related 1/4 mu omega skin depth. So these two terms are the same if you look at carefully, and N cross H is related with the surface current density. So now I will show you quickly how you can calculate the N cross H for specific example for TM. So if you look at the lecture notes from the last time, you will see that the transmitted power for TM modes in terms of the square integral of the Ez component. So let us look at the calculation of the N cross H. So for TM waves, the transverse direction of the fields is IK over gamma square, gradient of the transverse of the Ez component. H transverse could be obtained as a ratio of the impedance of the waveguide times Z cross E transverse. So for a guide, TM waves in the waveguide, so we can calculate the Z component of the field by solving the wave equation, which we do this for rectangular waveguide as an example last time. So, and we know that the transverse component of the field is related with the Z component. And once you know that the transverse component of the electric field, you can calculate that the transverse component of the H field. What you needed here, you needed to calculate the N cross H, and H is nothing but H transverse, because this is TM waves. So if you want to calculate this, you will get the following: 1 over Z0, and you have Z cross product Z cross E transverse square, and you know that the double cross product rule, so that is Z dot E transverse, that is equal to 0, minus Z dot Z along E transverse. So you will get 1 over Z0. This is, if we call this is A, B, and C, that is equal to A dot C along B, which is 0, and A dot B along C, that is nothing but the E transverse square. And basically what I am trying to calculate, so I'm sorry, I am trying to calculate the N cross H, N cross H, N cross H, and trying the absolute value square. So here this should be N cross H. So what is N? And so let us think in a minute. Let us think a little bit. n cross. Oh, okay. So sorry about this. So let us get this. Let me write this in open form. So this is equal to a dot c n dot e transverse along z minus n dot c e transverse square. So what is n? What is n? So what is n? What is n cross h? What is n? N is a vector perpendicular to the surface of the waveguide. Okay, sorry. Therefore, n dot z equal to 0, and that is nothing but 1 over z0, and absolute square is nothing but n dot e transverse square, and n cross h is this, square is this, and h transverse could be written from here, and this will be the following. So you will get the following. So if you take this, and this is nothing but the absolute square, you will get k square over z0 gamma square n dot gradient of the transverse Ez square. So basically, if you know that the Ez, you know that the Ez from the wave equation, solution of the wave equation, then you can calculate the n cross h, and n cross h, once you calculate the n cross h, you can integrate through the surface of the waveguide, then you can calculate the power loss per length, and once you calculate the power loss per length, you can calculate the attenuation coefficient. Okay, so you have the power loss per length, take the ratio, divide the 2 with the minus sign. That is the technique of calculating the attenuation coefficient. So I'm not going to do any more detailed calculation. You can study this for the other waves, TE waves, or you can go to the rectangular waves. You can work on the, for example, locus for the one of the modes of the rectangular waveguide. So before stopping for the waveguides, I can give you some numbers for the attenuation coefficient. For example, for a Cooper waveguide, so if the walls of the waveguide is Cooper, this attenuation coefficient is giving a distance such that the exponential drops to the 1 over the e to the minus 1 value, and that distance between 200 to the 400 meters. So that means that in 200 and 400 meters, the power, transmitted power, drops to the initial value times e to the minus 1. So at some distance, the initial value drops to the e to the minus 1, and for a typical waveguide for the Cooper, that number is around at the order of a few hundred meters. So for a few hundred meters, the waves are transmitted more or less perfectly, but at that time, at that distance scale, the amplitude of the power is decreased to the e to the minus 1 value. So that's all I want to talk about the waveguides. So let us go over quickly the cavities, and then start to the new chapter that will be the radiation. Do you have any question here? So I just sketch how you are going to calculate the attenuation coefficient. So idea is simple. First, our waves in propagation directions are plane waves. Since the walls are not perfect, our wave number has imaginary part. And our transmitted power goes with the E square or B square. Therefore, our transmitted power decreases by a square of the amplitude of the field. And that brings us e to the minus 2 beta z. And if the transmitted power in that form, you can solve this equation very easily and you can find the attenuation coefficient. And then we go to the what we know for the power loss per area for electromagnetic waves which they reflect from the walls of the conductor. We know that the power loss is related with skin depth times the n cross h. N cross h is nothing but the surface current density, and we calculate the n cross h for the surface current density for the TM waves. So, and we end up that the n cross h is related with the n dot gradient of the z component of the field. You know that how to calculate the z component of the field from the wave equation. Therefore, you can calculate the n cross h. Once you calculate the n cross h, and if you integrate this value through the surface of the waveguide, and you can find that the power loss per length, and then you can calculate the attenuation coefficient. The attenuation coefficients for Coopers are giving a distance for a loss of power exponentially as e to the minus 1 at lengths of a few hundred meters. So let us quickly go over to the cavity and what will be changed in the cavity. So in cavity, if you close the ends of the waveguide, you can create a cavity. And the only important change is the following: x, y, and z. Close the ends of the waveguide and make a cavity and say that at this point is a perfect conductor. So what will be changed? So let me put the this cylindrical cavity to the origin, and let's say that the d is the height, r is the radius, and the material in the cavity, let's say mu epsilon. So if you have a cavity and the waves inside the cavity, waves should satisfy the certain boundary conditions like in the waveguide. But in the cavity, you don't have a traveling waves because they are reflecting from the walls. What kind of waves you have in the cavity? Standing waves, like a cubic box you study in the quantum mechanics. You have standing waves. So if you have standing waves, if they are surviving as a standing waves, we call those standing waves as surviving at some resonant frequencies. Okay, so that is reasonable. So instead of e to the ikz, you have in that case sine kz and cosine kz. And these are the solutions, so they should be replaced by e to the plus minus ekz. These are the traveling waves, but if the two traveling wave meets, creates a standing wave, they are sine kz and cosine kz. And they should satisfy certain boundary conditions. So if we said this is the z equal to 0 and that is z equal to d, so at z equal to 0 and z equal to d, this K should be satisfied with certain boundary conditions, and the form of the K should be P pi over D, where P 0, 1, 2, 3. So we will understand this doing an example for the specific modes. But if you compare with the waveguides, K value for the waveguides are continuous. There was a cutoff frequency, but the values are the continuous. But in the cavity, K values, they should be discrete. Yes, right. This could be discrete. We can understand for a specific mode very, very easily. So since we start to work on TM all the time, this today and the last time, so let us go on with the TM, transverse fields for TMs. So for TMs again, Bz equal to 0, Ez is not equal to 0, and what kind of boundary condition you can put? One of the boundary condition, of course, the tangential component of the electric field at the cylindrical surface should be 0. That is reasonable. Ez should be 0 at the surface. Oh, that is understandable. The other one, when the wave hits the top or down, up or down, transverse component of the electric field, or what should be the transverse component of the electric field? So you have the electric field, let's say Ez, and E transverse. When you go to the surface of the cylinder, Ez should be vanished. How about the transverse? What boundary condition we can put for the transverse component? So do you understand what I am saying? So suppose that this is the electric field at any time of the electromagnetic wave. So it has component of E transverse and Ez. I know at the boundary of this, Ez should be 0. But if you go to the up or down, what should be the E transverse? Tangential component should be vanish also at the up or down of the surface of the cylindrical cavity. So what is the E tangential? For waveguide, E transverse, actually we derive I over gamma square K times gradient of the transverse Ez. Do you remember this? We are using this all the time. So Ez, we use the psi for TM or TE modes, but for TM, psi is nothing but Ez. So E transverse is related with the gradient of the Ez. But here you have a IK. Do you remember how the IK comes there? How the IK comes there in derivation? So we use the Maxwell's equations, we write the longitudinal and transverse direction to and a lot of things, but we said some point, instead of IK, instead of del over del Z, we substitute IK. Do you remember? Because that was plane waves. The original form is del over del Z. So since we are working in the cavity, I will replace the IK, the original term, that was del over del Z. Okay? So basically E transverse is 1 over gamma square gradient of the transverse del over del Ez over del Z. Del Ez over Ez. So I put instead of IK del over del Z, because I counted this point by assuming the plane waves, but we don't have the plane waves here. This is the original form. So then, what kind of solution you can suggest in order to satisfy the boundary conditions for TM waves? So for TM waves, you have Ez, which depends on some function xy, we don't know. And you have two options. One is the cosine, the other is sine. So cosine kz or sine kz. So which one is good for satisfying the boundary conditions? So since we don't have plane waves, we have cosine kz and sine kz. And what we require to satisfy the boundary condition up and down. Then which one is good, cosine kz or sine kz? Why sine kz? But z equal to no, because you have how many surfaces? You have the surface of the cylinder and up and down. So if you put Ez as a sine kz, you will calculate the transverse of the field by taking the derivative with respect to the z. What is the derivative of this? Cosine. Do you satisfy the boundary conditions at z equal to 0 and z equal to d? No. Okay, that is the tricky part. So you have to choose cosine kz. Then when you evaluate the transverse component, you will have sine kz, and then you have to satisfy the boundary at z equal to 0 and z equal to d. In order to satisfy the boundary at z equal to d, what should be the k value? So sine ka should be what? Sine ka should be what? NP. Therefore, k should be NP over d. We don't use the n because we are using in different purposes. Let's use a p. Okay. So basically, instead of k, you can put the discrete values pi p over d. So let me tell you again. So if you choose this solution, you should look at whether your solution satisfying the boundary condition. Take the derivative of this with respect to z. Then you will obtain cosine pi pz over d, and that is equal to 0 at the lower and the upper boundary. When z equal to 0 and z equal to d, sine p is 0. Okay. So once you know that the Ez, you can calculate that the E transverse. I am not calculating. And once you know that the E transverse, you can calculate the H transverse, like we did in the waveguides. 1 over Z0, Z cross E transverse. So the other thing, let us look at the resonance frequencies. So from the wave equation, we have a dispersion, and that dispersion, if you remember, that was gamma square was equal to mu epsilon omega square minus k square. So that was the dispersion relation. And k is not continuous in that case, that is discrete, and that is equal to what? Pi p over d square. So k is discrete. And if you solve that the frequencies, that is nothing but mu epsilon gamma square p pi over d square and take the square root of this, you will get that. So these are the frequencies corresponding to the resonant mode. So these are the frequencies which are surviving in the cavity. How we can get the gamma? How we can get the gamma? Gamma is coming from the solution of the wave equation. So if you remember that the wave equation was the following. So Laplacian of t and plus gamma square. For Tm mod, we have Ez equal to 0. Okay? So, how we obtain the gamma values? So, for this specific case, if you choose the cylindrical geometry, what is the Laplacian for the transverse? What is the, it is Cartesian, spherical, or cylindrical coordinates? Cylindrical coordinates, because you have a cylinder here. Then you can solve Ez, and at the surface of the cylinder, Ez should be 0. Okay? And if you solve this, you will find that. So that should be the Ez. You can call this as a Ez of xy. This is the z component. So, what is the solution of this? If this is the cylindrical coordinates, the Ez, depending on radial and azimuth components, is what? Some E0 and what else? What is the solution of this? So they are spherical harmonics, Basel functions, or what? Since it is cylindrical coordinates, they should be what? Basel functions. So they should be the Basel functions. So Basel functions has a order m and gamma mn rho e to the plus minus im phi. So gamma mn could be written as xmn over r is the radius. So if you write in that form, gamma mn is equal to sum xmn over r. If you substitute here, when rho is equal to r, you will obtain what? When rho is equal to r, you will get jmn xmn over r times r. And what should be this value when you go to the surface of the cylinder? When rho is equal to r, this Basel function should be 0. So we can determine the values of the xmn or gamma mn using the Basel functions. So the Basel functions has what? What is this? This is, we have these things. What are these? What is m in the Basel functions? We have two options, order and root. Is it order or root? Order. What are the Basel functions orders? Starts from where? 0 or 1? 0. So these are 0, that could be 1, 2. N is the root. That could be start from first, second, third. So basically these are the forms. as a function of what? Res rho j could be something like this. So let's say this is the j0, and this is the first root, this is the second root, this is the third root. So at these roots, Bessel function is vanishes and satisfy the boundary conditions. Now, generally, the surviving modes then could be written as omega. So the total square root says that 1 over mu epsilon square root of 2. Instead of gamma square, I can write x square mn over r square, and k square are discrete, that is pi square p square over d square, and the possible values are what? So the frequency depends on what? M and p. So you have several options. So M could be 0, 1, and so on. M could be 1, 2, and P could be what? 0, 1, 2, 3, and anything else. So these are the possible surviving frequencies in this cylindrical cavity. So the best example you can study the possible resonant frequencies in the cubic cavity. But one of the things I should tell you that this frequency, if you choose anything, depends on what? Depends on what? As a dimension. What dimension you have? 1 over r square, 1 over d. To take the simplest one, for example, p is equal to 0, then it depends on 1 over r. So the resonant frequency, or if you calculate the wavelength of the frequency using the resonant frequency, that is related with the what? The dimension of the cavity. So in nature, there is one cavity has the lowest frequency. What kind of cavity we have? That cavity is the surface of the Earth and the ionosphere. It's a cavity. And during the lightning, some resonance modes are occur. And observationally, the lowest frequency observed in the nature seen during the lightning events. And that is roughly 8 Hertz. Why it is the lowest frequency? Because the dimension is high, highest dimension in the cavity. So there are studies about this. You can look at from Google if you are interested in. The name is called Schumann resonances. Schumann resonances. So there are multiples of this, harmonics of this, but due to the dimensions, that is the lowest frequency observed in the nature, and they are seen during the lightning events, and they are mostly seen in the equator. That is discovered around 1960. But around 19, Tesla also discovered such frequencies. So before stopping, I want to say a few words about the cavity. There is one important quantity in the cavity it is used. Again, the walls of the cavity are not perfect. there is a terminology which gives the quality of these resonance frequencies. So that is called Q. And the Q is the following, definition of the following. The frequency of the resonance frequency, that could be any of those, stored energy and the power loss. This is a positive quantity if you do the carefully analysis. So that is a stored energy per power loss. Power loss at the surface of the cavity. So qualitatively, how you are going to calculate that the energy and the power loss? How you are going to store the energy and the power loss? So the stored energy could be calculated easily using the fields. You have the E and B fields. You can calculate the energy density integrated through the volume. Power loss could be calculated by the same formula we use. So if you remember that we write something for dP over the area, we said that was equal to what? That was equal to 1 over 2 sigma times the skin depth and cross H. So the power loss through the surface could be calculated this formula. How you can do? You have the n is the perpendicular to the vector to the surface of the cavity. You have the H fields, n cross H, and if you integrate this through the whole surface, you will get that the total power. This is power loss per area. If you integrate this through the area, you will get the total power loss. You know that the total energy and you can calculate the power loss, then you can calculate the quality factor of the given frequency. And for this specific example, if you want to calculate that the total power loss, you have to integrate this dE both sides, and then how many surfaces you have? Cylindrical surface, up and down surface. You have to integrate this, and you can calculate the quality of the cavity. So quality of the cavity you can calculate. For any oscillator, you can calculate the quality of the cavity. For dimensions, if you look at what are the dimensions? This is the energy. This is the energy per time, but frequency is the 1 over time. So this is a dimensionless quantity. For microwaves, this quality factor is around 1000. But for any kind of oscillator, you can calculate the quality factor of the oscillator. So now I am done for this chapter. We have seen that the interesting applications of the Maxwell's equations as a waveguide and cavity. And in the previous chapter, we see that the behavior of the electromagnetic waves when it reflect and refract through the different mediums which has the different refractive indices. Now we will come to the point how we were deal with what? Waves. Now we will deal with how the waves are generated, and that is the radiation. Okay, so next thing, in the next hour, I'll start with the radiation.